Okay, everyone, welcome back to the third video about the lecture material for week 1. Just to recap a little bit, in the last two videos, we gave a little bit of motivation why panel data sets are so useful. And moreover, we summarized the pooled least squares estimator. So we're still in a setting where we are not really exploiting the power of panel data. So we will now still continue with panel data models that do not contain any individual specific heterogeneity. However, we go away from the pooled OLS framework because now we introduce correlated variables correlated with the model errors, so endogenous variables. Okay, so I will start sharing the screen. So what we talk about now is the instrumental variable models in a panel data setting. So many of you probably know what instrumental variables are and why we need them in many cases. Yeah. So when do we rely on instrumental variables? Well, when we have some explanatory variable, so some observed variable that is of interest to us, and however, this variable is endogenous, so it's correlated with the error term. Now, why is that again a problem? Well, as we saw in the proofs for consistency of the pooled OLS estimator or OLS in general, if the error term is correlated with the axis, then we will typically have an omitted variable bias. And as you will see in the exercises, the omitted variable bias is not only a problem for the component that is endogenous, rather it also affects the other components of the least squares estimator. Okay, so now what do we do? Well, we normally look for so-called instrumental variables. And so those are variables that vary. So there's variation in this instrumental variable, and they are correlated with the endogenous variable. So if this varies, this thing varies, but these things have nothing to do with the response variable. Yeah? So, and because if this thing varies, this thing stands still or varies, but only through the channel of the endogenous variable. So when we say we have an instrumental variable, then we often talk about so-called exogenous variation. Okay, I will give some examples about instrumental variables in the following slides. So, but here's a little outlook. For good instrumental variables, we expect that they are relevant. So they have to be correlated with the endogenous variable, and they have to be exogenous, meaning that they have to be uncorrelated with the model errors themselves. Now, the most popular estimators are, well, the instrumental variables estimator, the IV estimator, and the two-stage least squares estimator. So for the IV estimator, we normally have as many endogenous variables as instruments, yeah, so the dimensions match. And for 2SLS, we have more instruments than endogenous variables. Okay, now what we will also see probably in the next video is that both the IV estimator and the 2SLS estimators are special cases of the so-called generalized method of moments. Now, GMM is something huge. It's really big because it's really so general. So many estimators are special cases of GMM. GMM was developed by this guy here, Lars Peter Hansen, a very famous paper. It's again in this highly cited ranking, pretty much on top. Yeah? And Hansen's contribution also gave him a Nobel Prize. Yeah? So, of course, you probably know that the Nobel Prize in economics is not really a Nobel Prize because Alfred Nobel, he hated both economists and mathematicians. So, in that sense, we are in very good company. However, this is like given by the Swedish Reichsbank. Okay, what else is to say about GMM? Well, we will talk again about that later. Maybe some gossip. Oh no, I'll leave the gossip for later. Okay, if you want to read about IV methods in Wooldridge, then you should take a look at chapters 5 and 8. So I think 5 is like the cross-sectional setting and 8 is the panel data setting. However, Wooldridge looks at 2SLS from a GMM perspective, whereas we here want to really stress that we have two stages and the two-stage least squares estimator. Then when we talk about GMM, we will actually motivate it and show why GMM is so useful, why it is optimal, and then proceed by showing that IV and 2SLS are special cases of GMM. But at the very first thing, we look at IV and 2SLS without even thinking about GMM. Okay, so we have a very simple IV model. So again, this response. Here we have a vector of unproblematic variables. And here with this y tilde, I denote a scalar variable that is potentially endogenous. So this variable here may be correlated with the model error. So you see this condition here holds. However, like this, it would be, of course, a problem for OLS. Now, our savior is this variable WIT, which we will call an excluded instrument. And for WIT and XIT, we have the following conditions. So these things are really endogenous. Wonderful. We simplify our exposition here a little bit, assuming that YIT tilde is a scalar. In principle, the same approach, of course, also works if this is a vector. Okay, so of course, y tilde is not included in the conditioning set here, because if it was included there, this would imply that y tilde is uncorrelated with the model error. Yeah? So here we explicitly say y tilde is correlated with the model error. Again, because X is actually exogenous, we can call this an included instrument, and oh, sorry, this should be actually WIT. So here we'll check that, I will change that. WIT is called an excluded instrument because it's excluded from the original model. Yeah, so we have two conditions that we need for a good instrument. Well, first of all, the relevance condition. So the instrument, the excluded instrument, must be correlated with the endogenous variable. And we have the validity conditions or the exogeneity condition that the excluded instrument is itself uncorrelated with the model error. Yeah, so now we will see that the relevance condition, this thing here, that can actually be tested because we just have to check a correlation between two variables and both are observed. And that's not so much of a big deal. The tricky one in application is normally the validity condition or the exogeneity condition. This can only be tested to a very limited extent. And we will talk about that thing when we discuss GMM and in particular the so-called J-test. Now, what does this validity condition require? Well, it requires that the instrument, WIT, is not allowed to have any direct effect on the response variable or any indirect effect through the omitted variables. Yeah? The only allowed effect on the response is really through the channel of the endogenous variable. Yeah? So the variation in WIT is allowed to induce some change in YIT, but only through the change in YIT tilde. Yeah? So it goes like this, up and then there. Yeah? But there cannot be any direct effect or any indirect effect through any other omitted variables that are relevant for YIT. This is sometimes called the exclusion restriction, and that is what people in applied papers spend a lot of time on, yeah, to make this exclusion restriction credible. Moreover, there should also not be some sort of a reverse effect. So there should not be any effect of the response variable YIT on the instrument WIT. Yeah, because, well, the first sentence rules out that WIT has an effect on YIT, yeah, because that is against the exclusion restriction. But of course, we also don't want to have it the other way around because this will create correlation and that's not good for the IV estimator. Okay, here are some famous examples of instruments. Yeah? So a classic in this course is that we want to know what is the effect of education on wage. Yeah, we discussed this quite a bit in the introduction because education is a classic endogenous variable because people choose their level of education. Yeah? So, and they choose it according to their capabilities, motivation, intelligence, call it whatever. And these are all variables that themselves have an effect on wage. Yeah? So education is clearly endogenous. Now, how to get rid of this? Well, a famous example is by David Card, who uses college proximity as an instrument for education. And well, here the idea is that if you live closer to a college, you're actually more likely to attend the college because it's less costly for you. So if you live far away from a college, you have to go to a city where there is a college, you have to pay rent, you have to, all sorts of costs appear, and therefore you are less likely to actually attend the college. Moreover, so this is kind of like the relevance. This actually can be checked. And the exclusion restriction here is, the idea is that, well, the place that you are born into is pretty much random, right? You don't have a choice there. And therefore, college proximity should give you a source of exogenous variation. Okay. Now, of course, this condition fails if people move closer to colleges to improve their children's chances. Yeah? So you could, for instance, think of parents that are highly educated, that make a lot of money, and they decide, okay, let's move to Boston because we have Harvard right around the corner, right? And of course, because these parents can give their children other advantages in their life, the exclusion restriction may fail because, like, college proximity may also have a direct effect on wages of the children in this case. Yeah, so you have to always be super suspicious. What you will also notice is that all these instrumental variables things, the famous examples, they are a little bit older already. Yeah? So back in the day, this kind of instrument went through. If you were trying to publish the same thing in nowadays AER, like the American Economic Review, one of the very best journals there is, you would probably have a problem. Another thing that helps is if you're David Card and you happen to be the president of the Economic Association. Okay. Anyway, we can use other instruments as well. So instead of college proximity, another famous example, I think this is from the Quarterly Journal of Economics, another really big journal. Angress and Kruger, they use quarter of birth as an instrument for education. Now, the idea here is that you have a tiny margin of exogenous variation because, well, in many US states, or also in Europe, in most countries, you are supposed to stay compulsorily in school up to a certain age. So for instance, they could say until you're 14, you have to stay in school. Yeah. And because the school year always starts at the same date in the year, but people are born in different points in time, this means that some people cannot leave school even if they would like to, whereas other people that were born slightly earlier or slightly later are allowed to leave school, so they drop out a little bit earlier. Yeah. And again, yeah, so that's pretty much it. So because their unobserved preferences don't play any role because these rules are compulsory, this should give you some sort of exogenous variation. Okay, now again, this is a paper from the 90s, really famous. And nowadays it is kind of seen a little bit more critically. For instance, there are some people that argue that quarter of birth may actually also have different, may actually affect wages through different channels. Yeah? So some people argue that there's some psychological effects for, like, being the oldest in class or the youngest in class and this kind of thing. So that may be there may be other channels. Yeah? So the exclusion restriction will be violated. And another thing that I think is a bit more interesting for this course, as it can actually be tested, is that this instrument may be too weak. Yeah? So the correlation between quarter of birth and the endogenous variable education is too low. And if you have weak instruments, this can cause all sorts of problems, and it can actually make the situation worse than just using OLS. Weak instruments, I find, is so interesting that we will actually investigate this in the exercises a bit more through a simulation exercise. Now, another thing to notice is that these IV estimators, they should only be interpreted locally. Yeah, so why is that? Well, if you do instrument the variables with a quarter of birth as an instrument, you will get an estimator for the effect of education. However, you should be very careful for which group in the population you interpret this parameter. Because the estimated effect of education, that is may not necessarily be accurate for individuals with university degrees, for instance, because for them, whether there's a compulsory schooling law or not, that doesn't actually matter, right? Once you're kind of 16 and you do a little bit more of schooling, it doesn't matter whether there's a law because you passed that already. Huh? So therefore, whatever estimate you get for the effect of education, this estimate is probably most relevant for people that are really on the edge, right? That either just dropped out when they were allowed to, or that could not. Yeah. Um, Good. Now, another very famous example. So you see that's again George Angrist from the MIT. This paper is also famous, I think, in the QJE, the Quarterly Journal of Economics again. We are again interested in earnings and wage, and we are interested in whether military service has an impact on earnings. Now, why is military service potentially endogenous? Well, if you decide yourself, okay, I want to join the military, that may be correlated with other factors that may also affect your earnings. And I only came up with here like the word discipline. That's what I think of when I think of the military. Um, Now, what Angrist does is that he uses data from the Vietnam draft lottery. So I'm not sure if you ever heard of this, but back in the day in the US, they actually had a lottery, and that lottery kind of determined whether you had to go to Vietnam or not. So, and because it was not necessarily your choice to go to Vietnam, this again gives you a source of exogenous variation. Now, another classic instrument in the migration literature is actually rainfall. But super popular, and it has been overused so much, and also in many contexts where rainfall is not a good instrument, that I say here that it's almost a meme. So you have to be careful if you use rainfall as an instrument nowadays. Okay, yeah, let's get a little bit more into the technicalities. So here we define this vector ZIT, which simply collects all the unproblematic variables. So this thing is uncorrelated with the error. This is uncorrelated with the error according to our exogeneity condition. We now have k+1 variables and k+1 parameters because we assumed that wi is scalar. So we could, of course, make it k plus p or whatever. Would not make much of a difference. And yeah, we can stack the ZITs together, that we like the same way that we did for pooled OLS, and this exogeneity condition then can be written like this. Moreover, if the instruments are all relevant, that also means that if we take the rank of this matrix here, it has full rank. So we want this thing to be invertible in the end. So like from our exogeneity condition that we have here, we have, well, we can call this a moment condition. So here we are. Now we replace this ui by the model, right? So ui can simply be written as yi minus xi times beta. So remember that xi is a t times k+1 matrix. So all the dimensions here match. And yeah, well, then we simply go through those equations. We replace ui by this part here, then we open the brackets, and then we simply solve for beta, and we see that this is the expression for the IV estimator. So it looks hopefully familiar to you. So for pooled OLS, we had like only x's here. And here we have like something that measures the correlation between X and Z. And here something that depends on the exogeneity of Z relative to the model error. Okay, now how do we estimate the IV estimator? Well, we use the so-called analogy principle. Yeah, so what does the analogy principle mean? Well, it means that whenever we see a population quantity, so for instance, a population average, a population mean, well, the expectation is simply an average over the whole population, right? We replace these things by sample analogs. So whenever we see a population mean, we replace it by a sample mean. That's all there is. And whenever we see a population variance, we replace it by a sample variance. That's the analogy principle. So quickly going back here. So this is what we want. We want to simply replace all the e's with sample averages, and there we go. Yeah, and like you really have to use the same arguments that we used for the pooled OLS case in order to show consistency and asymptotic normality. And because I hope that this was more or less clear on the slides and in the video, I left this as an exercise. Okay, I think that was it about IV. Now let's talk also about two-stage least squares. Now we go back to model 9. Where do we have model 9? Here. And the only thing that changes is now that, so this thing will still be a scalar, but our instrument is now actually a vector of instruments. So we have more instruments than we have endogenous variables. That is what I say here. Kind of the dimension of this matrix, so this is kind of the stacked matrix, is M, and this is bigger than K plus 1. Okay, so yeah, so Zi contains all the exogenous explanatory variables and the instruments. Yeah, we can then do two-stage least squares. So as I said, Wooldridge does this from the perspective of GMM. Here we kind of really want to stress the two stages. Now, what do we do in the first stage? From all the possible combinations of the instruments, right? I mean, once we have more instruments than endogenous variables, it is not clear which of the instruments we should actually use. Yeah. Now, of course, a very clear idea is that we should use the combination of the instruments that has the highest correlation for the endogenous variable, meaning that has the most relevance for this variable. Now, how do we do this? Well, it is actually pretty simple. We simply regress the endogenous variable on the vector that contains all exogenous variables. Yeah, so this ZIT again contains the XIT and it contains the instrument vector WIT. Now you simply use pooled least squares and you estimate this parameter gamma here. And with this estimator, you can then find the fitted values. So this is YT tilde with the hat on top, where you simply multiply the ZIT vector with the estimated gamma. Yeah, you see, this is simply the OLS estimator from this model in the stack notation. Now, once you have those fitted values, you go back to your original model and you run another regression. But this time you don't use the ZITs, but rather the ZIT tilde. And the difference between the ZIT and the ZIT tilde is that ZIT tilde contains the X. That's the same thing for both. But now here we don't have the vector of instruments, but rather only the fitted values from the first stage. Yeah, and because we have a first stage where we do some estimation, the model error in the second stage contains the original model error, and it also contains the residual from the first stage regression. Yeah, so that's why we changed the notation here slightly. Okay, when we do that, we can write the 2SLS estimator in the following way. Yeah, so this is simply again using OLS in the second stage. This will give you this form. And if I snack the data again, I can write it in a super compact form like that. Yeah. So the stacking procedure is exactly the same as the stacking procedure that we used in the pooled OLS estimator. You just have to be careful about the dimensions. Now, we can actually write the whole thing in a different way. And for that, we can simply use our intuition. So what is this Z tilde here? The Z tilde is the matrix that contains all the fitted value of the response variable using the instruments, right? So recall that this X tilde here, we see it here, this contains the X's and also the Z's contain the X's. Now, what is the best fitted value for X given X? It's X, yeah? So you fit X with itself and you fit the endogenous variable with the vector of all instruments, included and excluded. Yeah? And we can therefore simply write as, we can write the Z tilde as the projection matrix times X tilde. Yeah? So PZ has this very famous form. This is a projection matrix, and this maps the vector of like this matrix here of X's that contains partially the unproblematic XITs and the problematic YIT tildes. And this matrix takes this thing and maps it onto the column space of Z so that everything, so after you do this operation, there's only exogenous variables in there. Okay, now we're gonna take this expression and plug it everywhere where we see this Z tilde. So this looks complicated at first. So this is just copy paste. Everywhere we see a Z tilde, we plug it in. And we see that there's a certain simplification going on. So this thing here cancels with this thing. By the way, I'm hoping really that you can see my mouse because I'm moving, I'm marking stuff all the time. I hope you can see it in the videos. Anyway, so something simplifies here. And here we again have this matrix PZ. And therefore we can also write the 2SLS estimator directly like this. And this is also the version that Wooldridge uses. Now, what we can also see here is that for consistency of the two-stage least squares estimator, we will need another condition. Actually, in order to write it down, we need that this thing here actually exists. So we need to make sure that the expectation of Z prime Z has full rank and is therefore invertible. If that is not the case, then we say that beta is not identified. So because, well, what does not identified mean? It means that the data that we observe can be generated by several values for beta. So there is one value that can generate the data, and another value makes equally as much sense for generating the same data. So then it doesn't really make sense to talk about consistency or like a true value, because both of these values could be true. And if beta hat is consistent, well, which does it converge to? It's not clear. Nothing makes sense if you have non-identification. So identification comes first, and then afterwards we can talk about consistency and all these things. Okay, now this condition here that we just talked about, this was pretty obvious once we looked at this expression here of the 2SLS estimator. However, implicitly, we also assumed that when we made this two-stage procedure explicit. So this condition here is actually required also for consistency in the first stage regression, right? So remember what was the first stage regression? Here we have the ZIT tildes, which is basically what the matrix Z consists of. Okay. Now, what else? Yeah, so however, this rank condition, this thing here, it's not very restrictive, because it simply says that you cannot put in linearly dependent instruments. So you cannot trick the system by simply using the same instrument twice. That doesn't work. Now, if you have more than one endogenous variable, we can simply use this first stage for each. So that's one possibility of doing two-stage least squares with many endogenous variables. However, you should also kind of take a look at this chapter 8 in Wooldridge, because like the two-stage least squares approach that we used here is not the only one, even though it is a very popular version of the 2SLS approach. Now, I think, yes, this is the final thing that I want to say about instruments and 2SLS. What is the advantage of the two-stage procedure? Well, in the first stage, we can actually check the relevance of the instruments. So remember again, what do we do in the first stage, where we simply take the endogenous variable, y t tilde, and we regress it on all unproblematic variables, meaning on xit, which was endogenous, and the excluded instruments, wit, which were also exogenous. Those are exogenous, yeah, non-problematic. And well, if the WITs, the excluded instruments, are not relevant for explaining via t tilde, that would mean that beta 2 is 0 on the population level. So if WIT does not explain anything in via t tilde, then beta 2 should be 0. So therefore, an easy test for the relevance is that we test the null hypothesis that beta 2 is 0 versus the alternative that it's non-zero using a joint f-test, because this is of course a vector. Now, just rejecting the f-test at the normal level of significance, let's say 5%, is not enough. So in order to make sure that we have strong instruments, that we have good instruments, we need a large f-statistic. And there's an ongoing discussion in the literature what large f-statistic actually means. Now, I think Stock and Watson or Stock and Yogo, some famous people, they said a rule of thumb is that f hat should be bigger than 10. Now, so if you have only a single variable in the IV case, then you should have that the t statistic. So if this is not a vector, but rather a single instrument, then you would do a t-test on beta 2, and you should have that t hat is bigger than the square root of 10, which is almost like approximately 3.16. Where does that come from? Well, if you have a scalar, then the f statistic is simply the square of the t statistic. However, as I mentioned, this is still an ongoing debate in the literature, so weak instrument is still an active field, and you may even require a higher level of the f-statistic than this rule of thumb if you have a large number of instruments. Yeah? Because if you simply dump 2,000 instruments in the first stage, chances are that your f-statistic will be quite high, simply because there are so many actually irrelevant variables, but because of the sample correlation, you will find large f statistics. So normally, the higher the number of instruments, the higher should be your f statistic in the first stage regression in order to really prove that your instruments are not weak. Okay, I hope this was more or less understandable for you. As usual, if you have more questions, just let me know, write me an email. We can discuss further in the tutorials. And I see you in the next video for GMM. Bye.